K2, second keynote speech, technical, the instrument and death of security.
CEO of Counterpane Internet Security Systems, formerly Counterpane for all of those out there who read his cryptogram newsletter. He's going to be talking a little bit about sort of the business and security realities out there in the marketplace, how it's more process-oriented than necessarily strictly technically oriented. Ready to go?
I'm ready to go.
Okay, with that, I'd like to hand you over to Bruce Schneier.
Morning. It's interesting, a bunch of the things Marcus said, I sort of say also in my talk, so I actually wanted to go back and change a couple of things, but you get what I got. What I want to talk about is a lot of the same philosophy. What is the world like, and you know, how do we live, how do we do business given the realities of the world? And I'm not looking at the script kiddies per se, I'm sort of looking at the situation of vulnerabilities and attacks. Some of this I'm going to plow through pretty quickly, some of this I'll dwell on. So you may get my computer to work. All right, why do we care? It's worth putting this in context. The reason digital security is important is not for any reason of the internet. What we want to do, what we're all trying to do, is to move some of our, business and social constructs from the real world onto the internet. We want to have conversations, we want to have relationships, we want to do business. None of this is new and exciting, but it's a new area and we want to do that. And security is an enabling technology, whether it's privacy, authentication, integrity. These are all things we have face to face and we want them on the internet. And that's why security is important. What we're finding, as Marcus pointed out a couple of times, is that security as it exists is failing us. It's failing us regularly, sometimes pretty spectacularly. And the question to ask is, can anything be done about it? And how do we live in the world given that this is so? Now, I came to computer security from cryptography, and cryptography is math. And one of the things I said when I wrote Applied Cryptography is that we need to protect ourselves not with laws but with mathematics, which is sort of interesting but actually incredibly naive. Because what I've been learning over the past several years, looking at vulnerabilities, is that cryptography, the math, can't save us. Denial of service attacks, CGI attacks, most of the good attacks that we're seeing are not problems that cryptography, even if it was applied, could fix. So we can't say we're going to let the math protect us, because the math can't. A lot of these problems have nothing to do with the math. And oddly enough, they often have nothing to do with the technology. They're people problems. Now, cryptography is neat because you've got this key. And for every bit I add to the key length, it becomes twice as hard for the attacker to break it. So there is this imbalance between attacker and defender. A defender has an enormous advantage. Computer security is a lot more balanced. Someone finds a vulnerability, someone fixes it. And someone finds a new vulnerability, someone else fixes it. It's much more of an arms race than a mathematical trump, which makes it much harder to work with. And there's lots of problems in security everywhere. I mean, people will talk about this all week, so I won't even dwell on it. What's interesting is it's not just the security software. On today's networks, everything has a potential to compromise security. Right? We all knew that SendMail has to be secure. Suddenly we learned that Microsoft Word is a network critical application. Where did that come from? Right? In Windows NT, someone could write a rogue printer driver which would compromise your network security. You install a video game, it can compromise security. Suddenly everything's interconnected and everything matters. So we can't just say, we're going to secure the security critical applications. We're going to build good security software. Suddenly, everything is related and everything affects security. And this happened when a lot of people weren't paying attention. And it's got interesting ramifications. My prognosis for the future of products isn't very good. I'm not seeing things getting better. And Marcus said the same thing. I mean, defenses are getting better, but attacks are getting better. More things are migrating onto the internet, onto digital media, We're having a very target-rich environment. More people using the internet means the average intelligence of your users goes down. So we're having a less intelligent user base. And the big problem, and it was sort of my thesis in this talk, is that the future of the internet is complexity. And complexity is anathema to security. And that's really what I want to spend the next 20 minutes talking about. All right, let's do it in two sections. One, why are complex products insecure? I have 6 basic reasons. All right, the first one is security bugs. As anyone who's done code knows, faulty code is everywhere, right? Every code has bugs. Every program has bugs. Every product has bugs. But I have 2 examples. The Ariane 5 rocket, which was exploded a couple of minutes into launch because of a software bug, and the 2 recent NASA Mars missions, which were not shot down by Martian air defense, as some people might think. In one case, it was a problem converting metric and imperial units. That was a software problem. In the other case, it was another software bug that it caused the retro rockets to fire a few seconds too early when the craft was too high off Martian soil. You know, most security bugs are not this spectacular. You reboot Windows, so what? But you know, these are examples of even when there's a lot of money being spent doing it right, it's still possible and probable that you're going to get something wrong. All right, now good software needs to withstand random programming bugs, and there's a lot of work done in fault-tolerant software. And I like to call this programming Murphy's computer. You want to program a computer that makes random mistakes once in a while. Computer security is worse. I call it programming Satan's computer, and this phrase is from Ross Anderson. It's a really good one. Right, we're not building a system that has to withstand random faults. We're building a system that has to withstand malicious faults imposed on it by an intelligent and malicious adversary. Right? You have an intelligence that will make the retro rockets fire wrong every single time until you fix it. So it's not just random, there's an intelligence. And this is very difficult to do. Right? Security engineering is different than any other kind of engineering because most products are useful for their functionality. Security software isn't. Right? Security engineering is not how to make something work. It's figuring out how this might fail and preventing it. You can't just run functional testing. It doesn't work that way. In some ways, it's like safety engineering. But again, safety engineering involves random faults. Security engineering involves malicious faults. It's something Robert Morris Sr. said at a talk he gave. You have to build your system. You assume that your attacker is an integral part of your system and build your system anyway. That's what security engineering is. Okay, errors are used to attack systems. Right? We see this all the time. I won't go into details. And increased complexity means increased errors. And, you know, the rate we don't know, but certainly there are between 5 and 15 errors per 1,000 lines of code in normal commercial software. That's some of the best estimates I've seen. Most of them don't affect performance at all. Most of them you'll never notice. Some subset of them will affect security if they're exploited. So more complexity means more code, means more errors, means more security vulnerabilities. That just seems obvious. All right, number 2 is modularity. This isn't interesting. This is another one that snuck up on us. The old paradigm was you'd buy big behemoth packages of software and drop them on teeny operating systems. So you'd buy a word processor and you'd buy a spreadsheet and you'd run them all on DOS. The new paradigm is much more dynamic. Applications have components, DLLs, plugins. Plugins have plugins. So now you might buy a web browser and run a Java virtual machine on top of that, and run some kind of Java application on top of that, then have some rich content on top of that. So what you're building on your computer might be something that's never been seen before. Right? You can't assume that all the modules you download are trustworthy. You can't assume that even if they are trustworthy, that they will work securely in your configuration. You can't assume that even if they'll work securely, that the operating system will mediate that security properly. Remember, in the old paradigm, if applications communicated with each other, they did it through the operating system. So the operating system could manage that interface. Now plugins talk with plugins directly. The operating system doesn't get involved. Right? You can't assume that just because a module was tested for a particular application, if you use it for a different application, that it's secure. Ed Felton at Princeton makes a really good living taking secure Java applications, taking pairs of them that are both secure, putting them together, and causing insecurity. A really good example of how when you dynamically build your particular desktop, you might get in trouble in ways no manufacturer has ever envisioned, and in ways you can't figure out who to blame. Right, there are ways people are trying to mitigate this, the Java sandbox, the ActiveX paradigm. They have their own flaws. The third big problem is interconnectedness. This is another thing complexity brings us. And as systems get more interconnected, security flaws affect each other. Right? I talked about an MS Word problem suddenly affects everything on the internet. Right? Java applets that they get out of the sandbox can affect everything. Right? We saw a couple of weeks ago, it was a problem with IE and Microsoft Access that if you were running email, HTML email in like Java, in Eudora or Outlook, someone could compromise your system. So it's a very complex bug that involves multiple products, possibly from multiple vendors. Right? Things are now very interconnected. We saw a security bug in Napster. Suddenly Napster is now security critical. There are lots of game machines that have problems. Interconnectedness is a big problem because we don't know how things propagate. We don't know how things affect each other. And as things get more connected, they affect each other in very strange and new ways, and in ways we can test. Right? Other examples. There are games now which you download, and you can turn your game, your home machine, into a server on the internet. Have these games been checked for security bugs? Probably not. But you could be running a secure application, a secure business application, and maybe you or maybe your kid suddenly puts your machine on the internet as a server, and you're now vulnerable. You didn't know that. Right? Sun wants to have a home gateway network, and then put your thermostat and your refrigerator and your front door on the internet. Right? We're going to see Java now in cell phones. All of these things are going to have profound security implications that we don't understand. The SOAP protocol. Let's reuse network protocols for other things. So we can tunnel something over SMTP or SNMP. Yeah. How does that affect things? We don't know. Right? Connecting everything is really cool, but it makes security flaws much more dangerous because they can affect a lot more things. There's a book, I'm blanking, I think Charles Parrow is the guy's name. It's called, I'm now blanking on the title. It's called System Accidents. And what he talks about are highly nonlinear, tightly coupled systems, nuclear power plants, maritime shipping. And what he shows is that there are accidents that happen not because of anybody's mistake, just because the systems are so complex and so tightly coupled. And it's a fascinating book. His book's called Normal Accidents. Lots of case studies, talks about 3 Mile Island, where he'll say, look, after the fact, you can point to and say the operator made an error there, but if you go into the operator's shoes, he made the right decision given the information he had at the time. And it was the system itself, the 3 or 4 things failed that interconnected and caused this major accident. And we're seeing the same sorts of things on the internet, where lots of different things come to play. And this is going to get worse. The internet is the most complex machine mankind has ever built. It's highly nonlinear, and it's very tightly coupled. And we don't understand how it works. I mean, we understand how it's supposed to work, but we don't understand how it works. Reasons 4 and 5 are pretty easy. More complex systems are difficult to understand, which makes social engineering easier. If you don't understand what a certificate is, you can be spoofed with a bad certificate. If you don't understand how to check it, why you should check it, what it means, what it doesn't mean. If you don't understand what a digital signature is, you're going to write bad law. More complex systems are harder to understand, they're harder to configure. It used to be really easy for someone to configure a firewall. What were there, 7, 9 different protocols? But now there's over 100. And they're being used for much more complicated things. It's harder to figure out what to do. And more complex systems are harder to analyze. So if someone's trying to do a security audit, it's a lot more complicated. And the last one is complex systems are harder to test. And this brings us back to the first reason I talked about. Security is orthogonal to functionality. Just because a product works doesn't mean that it's secure. So what that means is no amount of beta testing can ever uncover a security flaw. You need to do actual security testing. And as products get more complex, that becomes harder. And what we're seeing, I mean, you sort of imagine someone shipping a product without any functional testing. Right? We all did this for our first computer science project, right? It compiled, we're done. Right? The odds of that not having bugs are basically zero. Similarly, if you don't do any security testing, the odds of your product not having any security bugs are basically zero. And as the number of features, the number of configurations, the complexity of your product goes up, the number of things you have to test goes up. And you really do have to test them all. If you have 20 different settings, each A or B, you're going to have a million different combinations. And you really have to test them all. But you're not. So you cut corners. You say, well, these 2 settings don't matter, so we don't have to test them together. You know, these 3 and these 5 don't affect each other. I mean, you're probably right, but in some cases you're going to be wrong. And we're at the point where we cannot adequately test the security products, let alone our networks. We just can't run them through all their paces. All right, second part of this is pretty easy. Products are getting more complex. I have a couple examples to show you. This is number of lines of code in the Windows operating system as a function of year. We see them go from 3 million to about 10 times that. The number of lines of code in Windows 2000 is still unknown. Microsoft was touting 50 million lines of code until the press started saying, ooh, that's way too big. Then they started touting 35 million lines of code. So, it's somewhere in the middle there. But whatever it is, it's much bigger than, Windows 3.1 was 3 million lines of code. It's getting a lot more complex. So if you look at the number of security bugs we're seeing in, let's say, the Windows 95, you want to actually expect it to at least double. This is the number of system calls in different flavors of Unix. Again, we're just seeing a trend towards complexity. The Windows number is a fake number. They define it differently. I mean, it's pretty impressive, but you don't look at that as, whoa, that's much more ridiculous. It's a different way of defining the term. This is the number of lines in different certificate protocols. Number of lines of ASN1 notation. I actually should put years on those. So complexity is creeping into everything. Right? I talked about Sun's home gateway, where complexity is going to creep into your appliances. Does anyone want their refrigerator on the internet? I mean, it sounds really fun until someone uses it as a launching pad for DDoS attacks. The new video game machines are now sold with an IP stack and a web browser. And it's okay for games, but I'm sure that Sony and Sega want you to do commerce on your game machine. Suddenly, that's now network critical. So I see 2 alternatives. One is to slow down and simplify. Right? We could, as a society, decide, whoa, the internet's way too complicated. We're going to do this right. Right? It takes 8 years for the FDA to approve a new drug. It could take 8 years for the government to approve a new version of a browser. Right? It sounds like zero fun, but we could do that. The other alternative, and the one I like, is to deal with it. Live with the fact that the products are insecure. Accept the vulnerabilities. Put processes in place that deal with it. And what I'm preaching here is sort of a shift from threat avoidance to risk management. Because that's what makes sense. The world is not secure. Right? We have technologies out there where anybody could kill anyone else they want. Yet we do pretty well as a society. Sort of why is that so? The reason that's so is we have processes in place. So let's talk about processes for the last 10 minutes or so. So the need. I just said that already. Security countermeasures are basically sold as prophylactics. right? Firewalls prevent network intrusion. Encryption prevents eavesdropping. PKI prevents impersonation. This is interesting, but if you go to the real world, no technology is sold that way. Right? You never see a door lock with the advertisement, "This lock prevents burglaries." It doesn't. That's not the way locks work. A lock is a lock on your door. It's a preventive technology, but it does not prevent burglaries. Similarly, safes don't prevent attacks. What you have, a safe's a good example, and this is Win Schwartz's example, and he does this very well. When you buy a safe, you're buying two things. You're buying the time it takes to break into the safe, and a barrier that prevents someone without the skill to break into your safe from breaking in. So if you are a bank, what you have is you buy a safe, and then you also have an alarm. Because when the safe crackers are at the safe breaking in, you want an alarm that rings, and you want guards that come running. So what you have is you have prevention, detection, and response. And together, those make a process by which we end up being secure in the real world. Right? Without detection and response, the preventive countermeasure only has limited value. Right? It works perfectly if it trumps the skill of the attacker, and it's a delay tactic if it doesn't. And in computer security, it's often a delay tactic of very small, because attack tools can be automated. Now, against some attacks, prevention is all you get. And this, for me, this is interesting because I came to this from cryptography. And cryptography is all about prevention. Because the model is the eavesdropping model. Alice and Bob and the eavesdropper. In that model, there's no detection, there's no response. Cryptography is all you have, so prevention better be perfect. And that works in that model. In the real world, in the internet we have today, that model doesn't hold. You have detection, you have response. Things are happening over time. You can't, the eavesdropping attacks are not the ones we're worried about. Right? And prevention in that model has its limitations. It can be very expensive. It's not perfect. Most of the time, detection and response are more cost effective. Right? It's much easier to hire a guard than it is to walk around in bulletproof armor. It's much easier for us as a society to have police investigate crime than it is to give everyone bodyguards. Detection and response work better. So the first part of this is detecting attacks. And the sooner we do this, the quicker, the better we end up being. The second part of this is responding. If we can just detect attacks, it doesn't do any good. Right? It's like a car alarm ringing in the inner city. If no one responds, it doesn't matter. So building systems to respond make a lot of sense. Right? Immediately we want to make the attacker go away. Longer term we want to prosecute. Even longer term, I actually believe in some of the stuff Marcus was saying about counterattacking. Vigilance is important. We can't do this 9 to 5, Monday to Friday. We have to do this 24 hours a day, 7 days a week. Right? Attacks happen at the worst possible time. Now, everyone remembers the Yom Kippur War, when the Arab nations picked the holiest day on the Jewish calendar, when the Jews supposedly weren't paying attention to launch their attack. That's what good attackers do. That's just smart. Last bit I want to talk about is insurance. If we're looking at it as risk management instead of threat avoidance, there are a lot of things we can do. We can reduce the risk, technically. We can accept the risk. And it's a perfectly reasonable thing to do. Being insecure and being in business is a perfectly reasonable decision to make. If you're more profitable than your risk is, you're happy. Or you could lay your risk off. You find someone who's willing to buy it. And then it's not your problem. As a CEO, if you're worried about someone stealing your customer database, you don't care if you solve that problem by making your network more secure or by insuring against it. Either way, you've managed your risk. And I believe insurance is going to be a big part of computer security. Just as in the real world, insurance drives real security. Now, the reason we have fire extinguishers and all the fire suppression equipment in this room is not because Caesar's Palace is magnanimous. It's because their insurance company demanded it. And you're going to see similar things on computer networks. If you are a business doing business on the internet and you want to get insurance, you have to have these security measures, these preventive measures, and this kind of detection, this kind of response. And that's going to be required. Right? This is not the military. We're all here doing business. And business involves risk. And those who embrace the risk do better in business than those that shy away from it. And so I want to see a more risk management approach to computer security. All right, just a few conclusions. So some of the things Marcus said also. Will we ever learn? Right, I have two examples. First one is buffer overflows. First identified in the 1960s, near as I can tell, first used to attack systems in the 1970s. We had the Morris worm, a very, very public buffer overflow exploit in 1989. So here we are today, some 35 years later, and 2/3 of all cert advisories are buffer overflows. And this is an easy one. There are tools out there to detect buffer overflows in software you write. Okay? We're trying to fix the hard problems, and the easy problems are still bothering us. Right? Example 2. This is a particular bug in Microsoft's IIS. It was identified, it was fixed in July 98. Microsoft released another warning in July 1999. Right? Two or so years, I guess, a year and a half later, January 2000, a bunch of websites are taken down by this this particular bug. So here's a problem that was identified, a patch was released, it was fixed, and it's still a problem. Right? The press gets this wrong. They sort of see it, there's a vulnerability, the vendor issues a patch, and then we're done. Right? You have to install the patch. A lot of people forget that, and Marcus said the same thing. I worry about the solution of automatically downloading patches, because stuff that automatically downloads could be good or bad. But that's one way to deal with the problem. We need to deal with this problem. I mean, things, even if they're fixed, aren't getting fixed in the field. Microsoft's not going to recall Windows 2000. But if this was another industry, that's what would happen. All right, limits are sort of 3 closing slides. The problem with good security looks the same as bad security. This is a big problem. Right? I can hold up 2 products. They use the same algorithm, the same protocols, the same buzzwords. One is secure, one isn't. You have no way of telling the difference. That's tough to work with. Almost all the security products on the market today are insecure. Actually, I think they all are. I think they all have major security vulnerabilities that we haven't discovered yet, some of which we know. I don't think that's going to change. I think it's going to get worse. The only way to survive in that world is to build processes that accept that reality and allow companies to do business anyway. On the other hand, we don't have to be perfect. Adequate security is often good enough. I got a document notarized last week. That is the most brain-dead security protocol I've ever seen. But it's good enough for a lot of things. Most systems in the real world permit some level of fraud. You look at Visa. They have billions of dollars of fraud per year. They are still very profitable. I was talking to the security guy who runs E-Trade. They have a really bad security system to authenticate you before you make trades. What he told me is, we haven't had a problem yet. If we have a problem, we'll just eat it. We're doing so much business. We'd rather have the barrier to trade on E-Trade be so low and be insecure than we would be secure. We'll accept that risk because it's more profitable. That's someone who's paying attention. And the third is the limits of technology. Security technologies are tools. They are essential for security, but they don't automatically convey security. And the social problems are a lot harder than the mathematics. They're a lot harder than the computer science. The social problems are the real problems. And we're not going to solve them with technology. So that's basically it. I have 2 announcements. Well, let's see. Actually, I have 1.5 announcements. Announcement 1 is I have a new book coming out in September, or maybe August. There's a flyer about it outside. It's a really cool book, and you'll like it. And announcement 2 is I'm still doing my newsletter. And I don't think I have time for questions either.